Hello and welcome back, everyone. We are on Chapter 7 in Fundamentals of Inorganic Glasses. Chapter 7 is devoted to the topic of density and molar volume. I know it's not the most exciting topic, density, but it's still important because, let's face it, nobody wants to carry around a smartphone that weighs 5 pounds. So we're going to be diving in now to a bunch of different properties of glassy systems, kind of each lecture devoted to one property, and today it is density and molar volume. So let's get started with the definition of density, of course. Density, given by the symbol here, rho, is simply the mass of our material divided by its volume. You will usually see this in units of grams per cubic centimeter because that is the most convenient unit for expressing density. But if you want to express it in SI units, then the appropriate units would be kilograms per meter cubed. Now, another related property is the molar volume. The molar volume here is denoted V, and this is how much volume that 1 mole of the material makes up. Sometimes it's more convenient to discuss in terms of density. Sometimes it's more convenient to discuss in terms of molar volume. And so it's important to be comfortable with using both of those. And the units here for molar volume are usually centimeters cubed per mole. So it's the amount of volume that 1 mole of the material makes up. And the conversion between density and molar volume is straightforward. To convert between these quantities, you just use the molar mass. The molar mass is in grams per mole, and that makes it easy to convert between density and molar volume. Now, the oldest and still very commonly used technique for measuring the density of glasses is called Archimedes' principle. This goes back to Archimedes, who very famously had a revelation while lowering himself into his bathtub and seeing how his body displaced the water and how the level of water was rising at the edges of the bathtub. He famously exclaimed Eureka and ran out around and wanted to tell everyone, apparently without remembering to clothe himself. So Archimedes' principle, which we still use, is based on the fact that the upward buoyant force that is exerted on a body immersed in a fluid is equal to the weight of that fluid that the body displaces. So just as when Archimedes lowered himself into the bathwater and the volume rose up, so the same thing with a sample of a solid material or a sample of glass. Archimedes' principle involves putting that material, putting that glass sample into a fluid. The fluid needs to be something that's going to be non-reactive with the material that is under study. In most cases, if you've got a glass that has reasonably good durability in water, you can use water for this and it will work fine. However, there are some glasses that will degrade rather rapidly in water. And so for those systems, you'd want to use some alternative fluid to use, like maybe an alcohol, for example. And the relationship here is that the ratio of the density of the object that you're measuring over the density of the fluid, that ratio is equal to the weight of the object divided by the weight of the displaced fluid. And so if you know the density of the fluid, you've measured the mass of the object, and you know the mass of the displaced fluid by measuring its volume, then you can calculate the density of the object. So this is a straightforward way to get the density of a glass sample. The things to watch out for are, first of all, as I mentioned, reactivity between the glass sample and the fluid. And second is make sure that you've got a good quality sample without any inclusions or blisters in the sample. Because if you have any like gas bubbles in your glass, that's those bubbles are going to have much lower density compared to the glass itself, and they're going to give you artificially low values of density. And so it's important to have a good homogeneous glass sample without any types of defects in it that could affect the density. One of the advantages of Archimedes' principle too is that you can work with samples with irregular shapes, and the fluid is just going to fill around that. So that is still a commonly used technique. Another variation on this that's a more sophisticated approach and can get you a better level of both accuracy and precision is pycnometry. Pycnometry uses an inert gas, which is typically helium, although it could be argon, for example. It uses that gas as the displacement fluid to determine the volume of the sample that is placed in the device. So usually a small sample, even just a few milligrams, is all that's needed to make the measurement. And it's got much more accurate and precise results compared to using just straight Archimedes principle. So with pycnometry, you can make use of a lot less sample, and you get really accurate results. And if anyone here, would like to use pycnometry, we have this available at our materials characterization laboratory at Penn State. And for those of you tuning in from other locations, be sure to check with your institution to see if it is available. Now, one of the features of glass is, of course, that it is a non-equilibrium material, meaning that the density and the molar volume depend on the thermal history of the glass sample. We saw this already in chapter 2 when we were discussing the volume temperature diagram, where we saw that the fast-cooled glass typically has a higher molar volume compared to the slow-cooled glass. A higher molar volume means that the fast-cooled glass would also have a lower density compared to the slow-cooled glass, which would have a higher density. And the reason for this is that the different cooling rates mean that the supercooled liquid is getting frozen in different temperature regimes. If it is frozen in at a higher temperature regime due to having a faster quench rate, that would be a higher effective temperature, labeled TF2, and then you'd end up with a higher molar volume compared to the slower cooled glass that has a lower effective temperature, because with the slower cooling rate, you're giving the supercooled liquid more time to stay in its metastable equilibrium before it departs from equilibrium and undergoes the glass transition process. So I just bring this up because when we're discussing density and molar volume, it's really not enough just to know the thermal history or just to know the composition. You also need to know the thermal history. And it's also important, if you're plotting the compositional dependence of density or molar volume, that you do so with consistent thermal histories to make sure that that's not a complicating factor that is messing up the interpretation of your results. Also recall from chapter 2 that there are a few systems that have anomalous volume temperature diagrams. Two of those anomalous systems are two of the most common substances on Earth, silica and water. Both silica and water, if you look at the liquid and or supercooled liquid volume versus temperature diagram, it goes through a minimum at some temperature, meaning it goes through a maximum in density before turning around and then basically evolving in the opposite direction at lower temperatures. For example, with liquid water, if you have liquid water above 4 degrees Celsius, when you cool it down to 4 degrees Celsius, it will shrink, and then it'll pass through a minimum in the molar volume, and continued cooling to temperatures below 4 degrees Celsius will actually lead to expansion of water. And therefore, this kind of reverses the usual the usual scaling of the molar volume with thermal history if you happen to be in that anomalous regime. So if you're in a very fast-cooled regime, you could be in this part of the diagram where the fast-cooled glass, as usual, has a higher molar volume compared to the slow-cooled glass. But if you cool in the regime such you're in this anomalous part of the diagram, then that relationship can be flipped, and the slower cooled glass could actually end up with a higher molar volume compared to the faster cooled glass. So that's Not the usual behavior, but it is something that we'd have to worry about for pure silica and with water. Now, when we consider four of the most common primary glass-forming oxides, these are some typical values of the room temperature density of these glasses that have been made under normal experimental conditions. Vitreous silica, SiO2, has a density of about 2.2 grams per centimeter cubed. Vitreous boron oxide has a density that's less than that, 2.0 grams per cubic centimeter. Germania, of course, has a structure similar to silica, but with a much heavier germanium cation. That has a much higher density, so that is 3.64 grams per cubic centimeter. Vitreous phosphorus pentoxide, P2O5, has a density that's just slightly higher than that of silica, 2.23 grams per cubic centimeter. Now, what happens if we mix some of these glass formers together? What I'm showing here are the densities of a mixture of boron oxide and silica and a mixture of germania and silica. So germania was starting out with a slightly lower density compared to silica. So if we start here with the density of pure silica as 2.2, and you just progressively add B2O3 to it, the density decreases with a fairly shallow slope as it approaches the density of B2O3. Germania does the opposite. So germania, if you progressively add germania to silica, the density will increase until it approaches the density of pure germania. Why this is important isn't so much for density as it is for refractive index, because if you're making waveguides from pure silica, you may want to either increase or decrease the refractive index of silica. And the most effective oxide to add to silica to increase the refractive index while maintaining really great optical transparency is germania. And the more germania that you add to it, the greater the refractive index will go up as the density also goes up. And if you want the opposite, you can actually lower the refractive index of silica by adding B2O3, which also lowers the density of the glass. Now, what if we add modifiers to silica? So adding modifiers to silica, this shows the density of silicate glasses, adding two different types of modifiers. So sodium oxide or potassium oxide. And these are measurements at room temperatures. This shows the density as a function of the mole percent of alkali oxide. And what we can see is that adding alkalis to pure silica increases the density. This is because pure silica has a rather open network, and the alkali modifiers go in and occupy some of the kind of in-between spaces. They're not truly interstitial spaces, but some of the more open spaces within the silicate rings and the network. The modifiers also act to convert bridging oxygens to non-bridging oxygens. That breaks up the glass network, which allows it to compress a bit more. So both of these things allow for the density of alkali silicates to be significantly higher than the density of pure silica. And if we look at the density trends among various binary silicate systems, what we see here are a bunch of lines that show what happens when you add various other components to pure silica. There are lots of different modifiers here, as well as a few other glass network formers. At the low end, you see that adding boron, B2O3, lowers the density of the glass. And in fact, that is, I think, the only one in this diagram that actually lowers the density of silica. The other one here is lithium. Lithium is tiny, so you might think that lithium would lower the density, but it's so tiny too that it fits in the open spaces within the glass network. So it's actually replacing an open space with a very tiny atom. And so that actually acts to increase the density slightly with respect to fused silica. What else? Other alkalis that get added, of course, increase the density. Alkaline earths will increase the density, and the heavier the alkaline earth, the greater the density increase will be. If you put in some um, especially heavy atoms like lead oxide, for example, adding lead to the glass dramatically increases the density. You can see that this density goes up to 6.5, 7.5 grams per cubic centimeter. So that's a very heavy glass. Um, what else? Adding, let's see, titania to the glass, that can also increase the density quite a bit. Now, one of the ways that we can analyze the molar volume is in terms of partial molar volume of different species. So if you consider um, your glass, say that we've got a binary glass, say a potassium silicate glass or a sodium silicate glass. Um, the molar volume is telling us how much volume that 1 mole of this takes up. We can ascribe part of that volume to the silica and part of that volume to the modifier oxides. And partial molar volumes are telling us how much the molar volume of the system is changing when we change the mole concentration of one particular component. So in other words, the partial molar volume, little v sub I, this is the partial molar volume of species I in the solution of the entire glass, is how much is the molar volume of the glass changing as you change the mole fraction of that particular species I while holding the temperature constant and the pressure constant. And therefore, one could write the entire molar volume of the glass as being a summation of the partial molar volumes of each component times the mole fraction of each of those components. So basically it's saying so much of this volume is due to this component or the next component or the next component. And if you add all those volumes together, that will get you the total molar volume of the system. So the way to get partial molar volumes is to systematically go through and change the mole fractions of specific species and measure how the molar volume is changing. What happens for borate glasses? So we know by now about the boron anomaly and the fact that if you were to take pure B2O3 and add a modifier like lithium to it, the first thing that happens is that boron converts from threefold to fourfold coordination. When it does that, the connectivity of the network increases and the density of the glass network is increasing. It's allowing for greater connectivity, less open space. And so there is this conversion from threefold to fourfold coordinated boron that increases the density of, in this case, the lithium borate glass. It's not really about the lithium so much as it's about the change in coordination state of the boron, which enables kind of a higher density packing of the glass network. Then when you get to about 1/3 mole fraction of the modifier oxide, so around 0.33 here. This is where we start to get a conversion of the boron from having a fully coordinated network to creating non-bridging oxygens. So some of the Q3 species are going to convert to Q2, and that causes some of the Q4 species to convert back to Q3 in order to maintain bonding preferences. So then the density is changing the other way. It's actually giving us a more open network with a lower density. So this is just another manifestation of the boron anomaly because of the two different structural roles that modifiers play in borate glasses. In this initial regime, converting boron from threefold to fourfold coordination, and then in this higher modifier regime where non-bridging oxygens are created. When we look at the density of alkali borates, it pretty much follows what you would expect here. This shows the room temperature density. We're adding the smaller modifiers here, lithium, sodium, potassium. This has the smallest increase in density. If you go to the larger ones like rubidium, cesium, silver, so that leads to a greater increase of density. We can also do density measurements at higher temperatures. So this would go into the liquid state here at 900 degrees C, where you can see similar types of trends. Now, density varies as a function of thermal history, it varies as a function of temperature, it varies as a function of composition, but it also varies as a function of pressure. This result shows the densification of B2O3 glass under pressure. And what this shows is increasing the pressure here on this top horizontal axis. On the bottom horizontal axis, this is the corresponding density that one gets from that increasing pressure. And then on the vertical axis, this shows the percentage of boron atoms that are in boraxyl rings. So remember, those boraxyl rings were these six-membered rings, and they have a more open structure. And so even though at low pressure, at atmospheric pressure, there's a high fraction of borons as members of boraxyl rings, as the borate glass is pressurized, those boraxyl rings are forced to break down so that the glass can have a more compact structure. And so the fraction of boraxyl rings is decreasing under pressure, and that's enabling an increase of the density of the glass. And you can see at these very high pressures, the density can actually increase quite dramatically. Interestingly, if you take a compressed borate glass, in this case, a compressed soda-lime borate, so sodium-calcium borate glass, and then anneal it, the density that is recovered isn't necessarily the same as what you started with, and that is a function of the pure non-equilibrium history of the glass. So here, for example, the dashed red line shows the density of the soda-lime borate glass prior to a high-pressure compression. And then the squares here show what happens after annealing that compressed glass again at its glass transition temperature under atmospheric pressure. And what one would expect is that if you anneal this for a longer enough time, this would relax all the way back down to the initial density. We don't quite see that, though, with these experiments because either not enough time was given for the annealing, or there is some complicated interactions between both the thermal history of this glass as well as the pressure history of this glass. On the other hand, with hardness, so this the blue axis here shows the Vickers hardness prior to compression. Under the same conditions, the original hardness is actually recovered after annealing for about 200 minutes or so. So it just goes to show some of the unique things that one can see with playing with not only the thermal history, but also the pressure history, or combination of temperature and pressure histories with the glassy state. Now, one of the most interesting things about density and molar volume of glasses is a phenomenon that is called polyamorphism. You're probably already aware of polymorphism in crystalline materials. Polymorphism is what occurs if you've got different crystal structures having the same chemistry, and because of those different crystal structures, the crystals can have different properties. So, for example, silica, crystalline silica, can exist in quartz forms, in cristobalite forms, stishovite, coesite, and so on. These each have different crystal structures, and therefore they give different properties. Even though they're exactly the same chemistry, they adopt different crystal structures under different temperature and pressure conditions in order to accommodate those temperatures and pressures, and that's what gives different properties. There is an analogous phenomenon in the world of non-crystalline materials called polyamorphism. This can occur in the liquid state and therefore get frozen into the glassy state. So some liquids can exist in two distinct liquid states, known as high density liquid, or HDL phase, and low density liquid, or LDL phase. For example, in this phase diagram here, you'd see polymorphism between these two solids, between these two crystals, but there could also be two different liquid phases, a kind of normal liquid phase that we see at low pressure, low density. This would be the LDL phase, the low density liquid, but there's a thermodynamic phase change, a first order thermodynamic phase change in going from the low density liquid to the high density liquid. The key is that there's some significant difference in the short range ordering of the liquids. These are both non-crystalline, and hence this is called polyamorphism instead of polymorphism, but it's still a thermodynamic phase change when going from one liquid to the other liquid, just like going from one polymorph of the crystal to the neighboring polymorph involves a thermodynamic phase change. Same thing when going between two different liquid states. Some examples of these are actually water and silica. Again, just as they have anomalous volume temperature diagrams, they also exhibit polymorphism under high enough pressure conditions. Some metallic glass forming systems have also been shown to exhibit polymorphism. And what this means is that if you quench a glass from a high density liquid versus a low density liquid, the characteristic short range ordering of the glass is going to reflect back to that liquid, whether it's the LDL phase or the HDL phase, and therefore the properties of the resulting glasses will be very different depending upon whether they originated from the high density liquid state or the low density liquid state. So this is not something that has been exploited industrially yet, but it's pretty interesting to consider the unique properties that one could obtain if you vary the pressure history of the glass and can expose glass to high enough pressures to actually see these types of phase changes in the non-crystalline regime. So that brings us to our glass great for the day, which is William Ernest Stephen Turner, W.E.S. Turner, who was a British chemist and a pioneer in glass technology who lived from 1881 to 1963. He joined the faculty at Sheffield University in 1904. Sheffield was and still is the center for glass technology in the United Kingdom. And recognizing the importance of glass technology at the beginning of World War I, Turner is the one who established the Department of Glass Manufacture at Sheffield in 1915. So he's the one who initiated this department at Sheffield University. Next year, it became the Department of Glass Technology, and Turner served as the head of that department until his retirement in 1945. So he was at the helm of the glass technology program in Sheffield for about 30 years. He's also the founder of the Society of Glass Technology, which he founded in 1916. This is the primary glass society in the United Kingdom, and it's also very international, much like the American Ceramic Society, for example. And he founded SGT to address the needs of industrial and academic glass research in the UK. He was also instrumental in setting up the International Commission on Glass in 1933, becoming its first president. And the International Commission on Glass is, of course, still the primary international organization in the glass community. So we have a lot of reasons to be thankful for W.E.S. Turner, who was really instrumental in bringing the International Glass Society as well as the British Glass Society to where it is today. All right, so to summarize this lecture, measurement techniques for measuring density and molar volume include Archimedes' principle, pycnometry, such as with helium. Molar volume can be expressed in terms of partial molar volume, and the density of glass depends on composition, temperature, thermal history, pressure, and pressure history. Next time, we are going to move on to Chapter 8 in the book. We're going to cover Chapter 8 in 2 lectures. The first will be devoted to elasticity of glass, and the second lecture will be devoted to hardness. So I will see you then. Thanks, everyone. Take care.